Welcome to Tomorrow Unveiled. I am absolutely buzzing today.
Oh, yeah.
I mean, usually I'm excited to get into the research, but
Okay.
this week feels different. It feels like the ground is shifting under our feet.
It certainly does. It's Saturday, January 24, 2026, and if you have been paying even a little bit of attention to the news cycle over the last 7 days, you know exactly why the energy levels are so high.
We are marking this moment right here, right now, as a historical inflection point. You know, for years we've watched those viral videos of robots doing parkour or dancing to 80s music or doing backflips.
hmm
And it was cool, it was entertaining, but it always felt a bit like a circus act.
It was performance. It was staged performance. That is the term we use. It was impressive engineering, don't get me wrong, but it was highly choreographed.
Right.
It wasn't messy. It wasn't real life.
But that era ended this week. We have officially moved from the era of stage performers to the era of
General purpose workers.
general purpose workers. Exactly. We're talking about robots that are actually physically shipping to factories and, increasingly looking like they might be heading to our homes.
That's the key, the transition from prototype to product. And our mission for Tomorrow Unveiled today is to really unpack what we're calling the physical AI flywheel.
The flywheel.
Actually,
I love that visual.
it is the perfect metaphor. We are seeing a convergence. On one side, you have hardware maturity, electric actuators that are stronger and quieter.
Okay.
On the other side, you have these massive software breakthroughs with vision language action models. They have converged to create what our research team is calling a ChatGPT moment for physical robots.
A ChatGPT moment for the physical world. That is a heavy statement. I want to challenge that right out of the gate, actually.
Please do.
Because ChatGPT moment is becoming a bit of a lazy metaphor. We hear it for everything. Is this actually a fundamental architecture shift? Or is it just better marketing for the same old robots with slightly better batteries?
That is a fair skepticism. And honestly, usually I'd agree with you. AI gets slapped on everything these days like a sticker. But in this specific case, the metaphor holds up because the underlying mechanism has changed in the exact same way it changed for text.
So break that down. Because for the last, 50 years, robotics has been a math problem, right?
Exactly. It was a geometry problem. We call it classical control or inverse kinematics. If you wanted a robot to pick up a coffee cup, you, the human engineer, had to be a dictator.
A dictator.
You had to define the world for it. Cup is at coordinates XYZ. You had to solve the differential equations to move the elbow joint here, so the wrist joint ends up there. It was all pre-calculated.
Which means the robot is dumb. It doesn't know what a cup is. It just knows go to coordinate X.
It's worse than dumb. It's fragile. If I move that cup 3 inches to the left, the robot executes the exact same math, closes its gripper at the old coordinates, grasps thin air, and the whole system fails. It has no perception. It's blind execution of rigid logic.
And that's why we've always had those safety cages in factories. Not just to protect us from the robots, but to protect the robots from the chaos of the real world.
Precisely. Now, enter the VLA, the Vision Language Action Model. This is the breakthrough. We are stopping the dictator approach and moving to an end-to-end learning approach. We aren't coding coordinates anymore.
So what are we doing?
We are feeding the system massive amounts of video data.
Okay, but how does a video translate to a motor moving? I understand how ChatGPT predicts the next word in a sentence. The cat sat on the tack out, and it predicts mat. How do you predict move arm left?
That is the magic. In a VLA model, the physical actions are tokenized just like words. The model watches a video of a human folding a towel. It analyzes the pixels, that's the vision part.
Right.
It associates those pixels with the concept folding a towel, that's the language part. And then, and this is the new part, it predicts the action tokens.
Wait, so it treats rotate wrist 10 degrees as a vocabulary word.
Essentially, yes. It turns physics into a sequence prediction problem. It looks at the current state of the world through its cameras and asks, what is the most statistically probable next movement to achieve the goal?
It's not solving a geometry equation.
No. It's making a probabilistic prediction based on millions of examples it has seen before.
That sounds incredibly inefficient computationally. I mean, doing math is cheap. Running a massive neural network to guess where to move your hand seems like overkill.
It is. It is massively compute heavy compared to the old way. But the trade-off is generalization. If the cup is moved 3 inches, the VLA sees the pixels have changed and predicts a different trajectory. It adapts.
Okay.
It has common sense about the physical world because it has seen the physical world in the training data, not because a programmer measured it with a ruler.
So we're trading raw efficiency for adaptability. Which leads us to this flywheel concept you mentioned in the intro. If these robots are learning like LLMs, do they need the same amount of data? ChatGPT read the whole internet. Do these robots need to experience the whole physical world?
They do, and that is why the deployment numbers we are seeing this week are so critical. It's the data flywheel.
The data flywheel.
Imagine you have one Atlas robot in a factory. It tries to pick up a wrench and drops it.
A failure case.
A failure case is a data point. In the old days, that failure just meant a technician had to come reset the machine. Now, that video of the drop, the sensory data from the motors, the force feedback, it all gets uploaded to the cloud.
Ah.
The central model, the brain, trains on that failure. It sees what went wrong. It adjusts the weights.
And then pushes a software update.
Oh.
Like on my phone.
Right. So the next morning, every Atlas robot in the fleet, whether it's in Detroit or Seoul or Munich, downloads the update. They all learned from the mistake that one robot made.
That's exponential. Humans don't do that. If I learn to ride a bike, you don't magically know how to ride a bike.
Correct. We have to learn individually through trial and error, one at a time. Robots learn collectively. This is what we call fleet learning. The rate of improvement isn't linear. It scales with the number of deployed units.
So the more robots you have in the field,
the faster they all get smart.
But there's a catch, surely. You mentioned the compute cost. Processing video from thousands of robots. We're talking petabytes of data here.
That is the bottleneck. That's the real challenge. We are seeing reports, and we'll touch on this with NVIDIA later, that the inference cost, the cost to run these models, is sky high.
Wow.
You need a supercomputer to run a factory now. It's not just plugging in a machine. You're plugging into a massive data center infrastructure.
So the barrier to entry isn't just buying the robot. It's buying the cloud compute to keep the robot smart. That feels like a significant shift in the business model of manufacturing.
It completely changes the economics. You're moving from a CapEx model, buy the machine once, to an OpEx model where you are constantly paying for the intelligence that drives the machine. But let's look at the machines themselves, because the hardware updates this week were just as significant as the software.
Let's do it. Let's move from the software brain to the hardware body, because all that intelligence is useless if the machine can't physically execute it. And the big headline this week, the one that broke the internet, was Boston Dynamics retiring the old hydraulic Atlas and unveiling the new, fully electric version.
Retiring is a polite way to put it. They effectively took the most famous robot in the world and sent it to the scrapyard in a very slickly produced video, I might add.
I think a lot of people were surprised by that. The old Atlas was an icon. It did backflips. It did parkour. It looked powerful. Why ditch a platform that was clearly working?
Because it was a research platform, not a product. There is a massive, massive difference. The old Atlas ran on hydraulics pressurized fluid-pushing pistons.
Right.
Hydraulics are incredible for burst power. That's why heavy construction equipment uses them. They give you that explosive jump for a backflip.
That's always a but.
But they are a nightmare to live with. They leak fluid. They require warm-up cycles. They are incredibly loud. If you've ever been near the old Atlas, it sounds like a lawnmower running in a closet.
Huh. I never thought about the sound.
And the efficiency is terrible. You're constantly pressurizing pumps just to keep it standing.
So it's the difference between a Formula One car and a Tesla. One is amazing for a lap. The other you can actually drive to work.
Great analogy. The new Atlas is electric. It uses high-torque electric motors actuators at the joints. No fluid, no pumps.
Which means it's quieter.
Much quieter, cleaner, and the parts count is drastically lower, which means it's easier to maintain.
But usually when you go from hydraulic to electric, you lose power, right? Electric motors can't usually match that raw hydraulic punch.
That used to be true. But looking at the specs from CES, the power density of these new electric actuators is absurd. They're claiming it is stronger than the hydraulic version in practical lifts.
Stronger? How much can it lift?
It can manipulate 110 pounds. That's 50 kilograms.
That's a heavy lift for a humanoid form factor.
Yeah.
That's more than a lot of people can lift safely.
It is, but the strength isn't the part that freaked people out. It was the movement. Did you see the reveal video?
Oh, the Exorcist moment. Right, yeah, I think everyone saw that. The robot was lying face down, and instead of getting up like a human, pushing up, turning over, it just folded its legs backward over its head and stood up in reverse.
It was unsettling, wasn't it?
It looked broken. It looked like a glitch.
Yeah.
My first thought was, oh no, the demo failed.
But it was pure efficiency. And this is a major design philosophy shift. For years, we tried to build biomimetic robots that move exactly like humans because they are replacing humans.
Right, makes sense.
The new Atlas designer said, Why?
Why inherit human limitations?
Exactly. Humans have joints with limited range of motion. We have knees that only bend one way. We have necks that only rotate, maybe 90 degrees each way. The new Atlas has 360-degree fully rotational joints. It doesn't have a front or a back.
Which completely changes the geometry of a factory floor.
It does. Think about a brownfield factory, an existing auto plant built in the 1980s. The aisles are narrow, there are pillars everywhere. If a human needs to turn around while carrying a heavy box, they need a turning radius. They need space to pivot.
And the Atlas just rotates its torso 180 degrees. The legs stay planted.
The legs stay planted, the head spins around, the arms flip over. It requires zero turning radius. It can operate in spaces even tighter than a human can. It's optimizing for the task, not for the human aesthetic.
It's almost arrogant. It's like the robot is saying, I don't need to look like you to do your job better than you.
It's utilitarian, but it does raise that uncanny valley feeling. When things move in ways that biology doesn't allow, our lizard brains panic a little bit.
Panic is right. But let's talk about deployment. Because Boston Dynamics has been showing off robots for a decade. Is this one actually going to work, or is it just going to dance in YouTube videos?
That is the billion-dollar question. But the partnership with Hyundai suggests it's real this time. They are deploying these into the Hyundai Meta plant in Georgia this year.
That's a live auto manufacturing plant.
It is a very advanced one. And they aren't just going to be in a cage welding something. The goal is for them to move parts between stations to work alongside the line.
And that's where the brain comes in.
This is where that Gemini robotics brain comes in. The partnership with Google DeepMind.
Right, because the robot needs to know what it is carrying. It's not just go to position X.
The example in the technical report was fascinating. You tell the old robot, go to bin A. It goes to bin A. If bin A is empty, it stands there forever. It fails.
Right. It's stuck.
The new Atlas, using Gemini, can be told, get me the strut for the left suspension. It looks in the bin. If the bin is empty, it looks at the table nearby. It reasons that the part might have been misplaced. It has a concept of object permanence.
Common sense.
It's the holy grail of robotics, handling exceptions without crashing. If they can actually pull that off in a live factory, well, the labor economics of the entire automotive industry change overnight.
But that if is doing a lot of heavy lifting right now.
Massive lifting. We haven't seen it run a full shift yet. We haven't seen it handle a dirty lens or a network outage or a drop tool. The demo is always perfect. The factory floor is always messy.
Speaking of brains that can handle the mess, we have to talk about NVIDIA.
Oh, yeah.
Because if Boston Dynamics is building the body, NVIDIA seems hell-bent on building the mind, or at least the tools to build the mind. This week, they announced the Alpamayo family of open-source models.
NVIDIA is playing the platform game, and they are playing it to win. The headliner is Alpamayo 1, a 10 billion parameter reasoning VLA model.
Yeah, there's that word again,
Yeah.
reasoning. But NVIDIA is doing something specific here called a reasoning trace. Our research team flagged this as a critical solution to the black box problem. Can you break that down? Because black box sounds like something from an airplane crash investigation.
It's actually a similar concept, and this is crucial for anyone worried about safety, which should be everyone. Usually with deep learning AI, like the VLA models we just discussed, the input goes in and an action comes out. We don't know what happened in the middle. It's a black box. The neural network made a billion tiny calculations, but we have no visibility into why it decided to turn left instead of right.
Which is a nightmare for regulators. If a self-driving car swerves into a fire hydrant and you ask the manufacturer why, and they say, we don't know, the math just did it, that's a lawsuit waiting to happen.
Exactly. It makes the system unverifiable. Alpamayo changes this by generating a reasoning trace. It literally verbalizes its step-by-step logic in human-readable text before or during the action.
So it's narrating its own inner monologue.
Yes. So before it acts, it might generate a text output that says, I see a child running toward the street. The road surface appears wet. Friction is reduced. I must apply brakes gradually to avoid skidding.
So it tells you why it's doing what it's doing. That feels huge for debugging.
It's massive. If there is an accident or just a weird behavior, engineers can look at the trace and see, oh, look here. It identified the fire hydrant as a child because of the red code. It makes the system debuggable. It allows us to audit the thought process of the machine.
That feels like a prerequisite for having these things walking around us. I wouldn't want a robot in my house if I couldn't ask it, why did you just put my cat in the laundry basket?
And ideally, the reasoning trace would tell you the cat was sleeping on the dirty laundry and I failed to segment the two objects.
Okay, that's a terrifying example, but helpful. Now, speaking of testing these failures, They aren't just testing on the road, right? Because waiting for a robot to accidentally grab a cat is a bad testing strategy.
Horrible strategy. Testing in the real world is too slow and too dangerous for the volume of data they need. To solve the long tail of weird events, they introduced AlpaSim.
AlpaSim.
It's a digital twin environment simulating millions of miles.
I saw the stats on the dataset they released, the physical AI open datasets.
It's massive, 1,700 hours of driving data from 2,500 cities. But it's not just highway driving. They are focusing on the long tail.
Define long tail for the listeners who might not be in stats.
In any distribution of events, the head is the common stuff. Driving straight, stopping at a red light. You can get data for that easily just by driving around.
Yeah.
The long tail is the weird stuff that happens once in a blue moon. A parade float breaks down in the intersection. A kangaroo jumps on the highway in a snowstorm.
The stuff you can't predict.
Exactly. You can't verify safety by just driving around hoping a kangaroo shows up. But in AlpaSim, you can spawn 1,000 kangaroos. You can simulate the erratic pedestrian behavior, the extreme weather, the construction zones with confusing signs. You can run those scenarios millions of times to train the brain.
It's like the Matrix for robots. They learn kung fu or safe driving before they ever plug into the real world.
A very apt analogy. And it allows them to compress years of learning into days of computing.
Before we move on to the robots that are trying to get into our living rooms, Figure AI. I want to take a quick second. If you are finding this breakdown of the AI flywheel useful, specifically for our listeners on YouTube, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button. It helps us reach more viewers who are trying to make sense of this shift.
And be sure to turn on notifications. The news cycle is moving so fast that missing a WEC feels like missing a year.
It really does. And for our audio listeners on Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and a review for Tomorrow Unveiled. It helps us climb the charts and keep doing this deep research.
We do read the reviews too. We love seeing what resonates, so yes, please do.
Okay, Section 4. The Domestic Frontier. We talked about Atlas in the factory. But Figure AI is making a play for the home, and they're taking a very different approach with Figure 03.
This is where the design philosophy diverges completely. Atlas is an industrial machine. It looks like a machine. It's naked metal and plastic. Figure 03 is designed to be around people in their personal space.
Right.
And the biggest change our research team noted is soft goods.
It's wearing clothes.
Essentially, yes. The robot is covered in a specialized fabric. It's not hard metal or plastic on the outside.
Why? Is it just fashion? Are they trying to make it look less like the Terminator?
It's partly aesthetics. It looks less dystopian, more approachable, but it's highly functional. First, as any parent knows, soft things are safer.
The bumper car principle.
Right. If you bump into a metal robot in a narrow hallway, you're going to get a bruise. If you bump into a fabric-covered, padded robot, it's like bumping into a firm sofa. It drastically lowers the risk of injury in a domestic environment where kids and pets are running around.
Plus, it protects the robot itself from scratches and dings.
It does. But there is another functional benefit: weight. The research team noted it is 9% lighter than using hard casing.
9%, wow.
Lighter robots mean longer battery life and less momentum if they do fall.
And practical maintenance, too. If the robot spills coffee on itself or if the baby spits up on the robot, you can just change his shirt.
Washable robotics. It sounds mundane, but that is a critical feature for a home appliance. You can't just hose down a $1 million robot.
That makes so much sense. But being soft isn't enough. You have to be gentle. And they've upgraded the hands, too. The tactile sensing stats blew my mind.
Fingertips that can detect forces as light as 3 grams.
That's the weight of a paperclip.
Precisely. Why does that matter? Because in a home, you aren't lifting 110-pound engine blocks like Atlas. You are picking up a wine glass. You are holding an egg. You are handling a child's toy.
Right.
You need gentleness, not just brute strength.
This is the difference between position control and force control, right?
Yes. A standard industrial robot moves to a position. If a wine glass is in the way, it moves through the wine glass, it crushes it. A robot with high-fidelity tactile sensing feels the resistance of the glass and stops applying pressure. It feels the object.
Wow.
If you can't feel the difference between 3 grams and 300 grams, you are going to break everything in the kitchen.
And the charging. I saw something about this. No more plugs.
Wireless charging. The robot walks onto a mat and charging coils in its feet handle the power transfer.
That is so slick. It just goes to its corner and stands there. It feels very Consumer electronics, very Apple.
That is the goal. To make it an appliance, not a science experiment. You don't plug in your Roomba manually. It finds home. Figure is applying that same logic to a humanoid.
And the brain. It's using something called Helix.
Yes, the Helix brain. And again, the learning curve is the story here. The robot learned to fold laundry, specifically towels, from just 80 hours of video footage.
80 hours. That seems fast, but also slow. I feel like I've spent more time than that trying to teach my kids to fold laundry, and they still ball it up.
It is remarkably fast for an AI. And unlike your kids, once the robot learns it, it never forgets. It doesn't get bored. It doesn't complain.
But laundry is notoriously hard for robots, isn't it? Because fabric is deformable.
It is the hardest physics problem. A rigid box is easy. It has corners. A towel changes shape every time you touch it. It flops. It wrinkles. For a robot to understand the state of a crumpled towel requires incredible perception. The fact that Helix learned this in 80 hours validates that VLA approach we talked about earlier.
And Figure AI isn't playing small. They're building a factory called BotQ, aiming for a capacity of 12,000 robots a year.
12,000! That's mass production. That's not a boutique research lab. It is a clear signal that they believe the technology is ready for scale.
So we have the factory worker, Atlas, and the home assistant, Figure. But we have to look at the competitive landscape. Because it's not just these two.
No, it's not.
Section 5, the competitive landscape in manufacturing reality.
It is getting crowded, and we have to talk about Unitree.
The price disruptor.
The Unitree G1 model. Our research team found the pricing is around $16,000.
$16,000.
Facts.
I mean, that's the price of a used Honda Civic for a humanoid robot.
A capable one, too. They demoed it doing martial arts, high-speed punches.
Which is terrifying, but impressive.
Their strategy is different. They are commoditizing the hardware. They want to flood the market with affordable, standardized hardware and let developers build the apps. It's the smartphone model.
Build the iPhone. Let someone else build Angry Birds. Except Angry Birds is folding my laundry.
Or guarding your warehouse. Or patrolling a perimeter. By lowering the cost of entry, they're trying to capture the developer ecosystem.
But then there's the elephant in the room.
Yeah.
Tesla. Optimus. We can't do a robotics edition of Tomorrow Unveiled without talking about them.
We can't. And there was an update on the Cybercab and Optimus this week. It was a classic reality check on manufacturing.
The S-curve.
Yes. The warning was that initial production will be agonizingly slow.
Which, to be fair, is true of almost every new manufacturing process. I think people forget how hard it is to build things from scratch.
We call it the valley of death in manufacturing. You spend a massive amount of time and money setting up the line, calibrating the machines, and the output is tiny. You are just bleeding cash. But the promise is that once the process is dialed in, it shoots up. It becomes insanely fast.
Our research team made a point to note this as impartial reporting. This isn't just a Tesla problem. It's a physics problem. Even if they plan for 30,000 units, getting the first 500 perfect is the bottleneck.
Exactly. We have to separate the hype of millions of robots from the reality of getting the first 100 to work reliably. It takes years to climb that S-curve.
Speaking of reliability, we have to talk about the butlers. LG Celoid.
Ah, yes. The wheeled humanoid.
It's cute. It rolls around. It's part of the smart home ecosystem. But the field reports say
Yeah.
it's a bit of a toddler.
It can fold laundry, but it takes 2 minutes per towel.
2 minutes. I can fold a towel in 4 seconds.
And that is the gap between possible and practical. The vision is zero labor. But right now, the utility cost, the time it takes, is higher than doing it yourself.
It's the dishwasher problem. If loading the dishwasher takes longer than washing the dishes by hand, people won't use it.
Precisely. But remember, the first dishwashers weren't great either. This is generation 1. The speed will come with software updates. That's the hope anyway.
Okay, we've covered the serious stuff. The factories, the homes, the brains. Now I want to get into the weird stuff.
My favorite part.
Section 6, Weird Science. Because the academic papers this week were wild.
This is often where the real innovation happens, on the fringes.
Let's start with the detachable hand. This comes from EPFL and MIT research.
This is a brilliant, if slightly unsettling concept.
Describe it for the listeners, because it sounds like something out of a horror movie.
Okay, imagine a robotic arm with a hand. Standard stuff. But then the hand, it just detaches. It disconnects from the wrist.
And then
And then it crawls away on its fingers, like a spider.
thing from the Addams family.
Exactly. It uses a symmetric design, which means the fingers can bend fully backward and forward, so it doesn't matter which way is up, it can just scuttle.
And it crawls where?
It crawls into a narrow pipe or under heavy furniture where the whole arm can't fit.
It grabs the object.
It grabs the object, crawls back to the arm, and reattaches itself.
That is incredibly useful and absolutely nightmare fuel. But I see the application. If I drop my keys behind the couch, the robot doesn't need to move the couch. It just sends his hand in.
It creates a modularity that we haven't seen before. It blurs the line between manipulator and mobile robot. Usually the hand is just a tool. Here, the hand is a robot in itself.
Okay, next one. Stingray physics.
Yeah.
UC Riverside. This one is underwater.
This solves a huge problem for underwater robotics. Usually, if you want a robot to inspect the ocean floor, say, for internet cables or coral reefs propellers, stir up all the sands and sediments.
So the robot blinds itself.
Right, or the suction from the water flow sucks the robot down into the mud. It's called the ground effect. It's a real pain.
So what do the stingrays teach us?
The researchers found that stingrays naturally experience this negative lift, this suction pulling them down. But they use a specific wave motion and undulation to neutralize it.
They surf the suction.
In a way. They discovered that by adjusting the fin angle just a few degrees, they can cancel out the suction. This allows for new autonomous underwater vehicles, AUVs, that can glide inches from the seabed without disturbing a single grain of sand.
That is huge for ecology, inspecting sensitive ecosystems without destroying them.
Nature has had millions of years of R&D. We are just catching up.
And finally, let's talk about faces. Columbia University.
The uncanny valley problem.
Robot faces are creepy. We all know it. Stiff lips, dead eyes.
Yeah.
It's just...
Off. So Columbia researchers built a robot that learned to lip sync. But here's the cool part. It learned by watching itself in a mirror.
like a teenager practicing for a date.
It watched itself, and it watched YouTube videos of humans speaking. It used a VLA model, vision to action. It connected the sound of a phoneme, the sound of an O or an E, directly to the motor movement of the lip needed to make that shape.
So it's not hard-coded. It's not an animator moving sliders.
No. It learned the physical correlation between sound and shape. This creates fluid, human-like speech movements, not the creepy puppet mouth we're used to.
Why does this matter? Is it just for aesthetics? To make them less scary?
No, it's functional. Think about the Tombot Jenny, that therapy dog we mentioned on a previous Tomorrow Unveiled for Dementia Patients, or nursing home robots. If a robot is taking care of a human, emotional connection is functional. Nonverbal cues, a smile, a sympathetic lip movement build trust. If the face is a stiff mask, it creates anxiety.
So making them less creepy actually makes them better at their job.
Exactly. It's a feature, not a gimmick.
Wow. Okay, we've covered a lot. From electric factory workers to crawling hands to lip-syncing robots. Let's bring it home. Conclusion.
If there's one takeaway from this week in January 2026, it is this. We aren't just building tools anymore. I want to quote Brett Adcock, the founder of Figure AI. He said, "We are building a new species."
That gives me chills. A new species.
It sounds hyperbolic, but look at the evidence. We have 360-degree joints. We have soft, tactile fingers that can feel a paper clip. We have brains that can reason and explain their logic. All of these converged this very week.
It's not sci-fi. It's shipping. But the challenge ahead isn't proving the tech works anymore.
No, the science is done. The engineering is mostly done. The challenge now is the scale. It is that agonizingly slow ramp of manufacturing. It is the massive data processing infrastructure needed to keep that digital nervous system running.
It's logistics. It's supply chain. It's power grids.
It is the boring stuff that actually changes the world.
I want to leave the listeners with a final thought. We talked about the flywheel, the digital nervous system.
Yes.
If robots are now learning from video and sharing that knowledge instantly across a fleet, consider this. If a robot in Tokyo learns how to peel a mango today and that data is uploaded to the cloud, processed and pushed out,
then our robot in New York knows how to peel a mango tomorrow. Instantly.
we are witnessing the birth of collective physical intelligence.
Exactly. Humans don't work like that. If I learn to play piano, you don't magically know how to play piano, but they do.
So what happens when the collective knowledge of physical work exceeds what any human can learn in a lifetime? What happens when the fleet knows everything?
That is the question that will define the next decade.
Something to chew on. All right, that's it for this week's exploration for Tomorrow Unveiled. What a week.
It's been a wild ride.
We love hearing your thoughts.
Yeah.
Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this new era of robotics. Which robot would you welcome into your home? The fabric-covered Figure 03 or the spider hand crawler?
Don't choose the spider hand, please. I am begging you.
Leave a comment, let us know. Thanks for listening to Tomorrow Unveiled. We'll see you in the future.
Goodbye, everyone.